All right. Okay. So today we'll discuss a very simple principle in mathematics called the pigeonhole principle. So that's the start of today. Okay, the pigeons. You see pigeonholes. The statement is extremely simple. Even 5-year-old kids can understand the principle and do something with it. So you can see in this picture, maybe too small, but let me bring it up to see it. Let you see it. Okay. So is it big enough? So in this picture, there are 9 pigeonholes, but there are 10 pigeons. So what can we say about it? So if the picture shows at least one pigeonhole will be occupied by 2 pigeons. Of course, there are another way is one pigeon has to go away if each pigeonhole only allow one pigeon. All right. So that's pigeonhole principle. All right. Of course, in general, we may have n pigeons and k pigeonholes. And then what it means is at least one pigeonhole will have n over k pigeons. Of course, we take the ceiling. If 5 pigeons, 3 pigeonholes, 5 divided by 3, it's roughly 1.7. So the number of pigeons should be integers, so will be 2 instead of 1.7. Okay, so that's what the ceiling means. And one special case is when we have more pigeons than pigeonholes, one pigeonhole will have at least 2 pigeons. It's very, very simple. All right. Usually we use balls for pigeons and boxes for pigeonholes. Of course, mathematically, this is not a rigorous statement. To be rigorous in mathematics, we'll state it in terms of functions. So what we mean is for any function, so that's one for any function, all right, from A to B, where A has n elements and B has k elements. So we assign each element inside the A to an element of B. Right? So for any such assignment, some element of B will be an image of at least n over k elements. So some elements inside A will be signed, at least this many elements of A will be signed to an element of B. So if you look from left to right, from right to left, in that case, this element have at least three images. So these 3 elements assigned to this one. So mathematically, we state it this way. All right. So that's very, very simple. And the proof is it's trivial. It's very easy to prove it. However, such a simple statement, it's very, very powerful. Later on, I will show you some elegant and amazing application of this one to prove something extraordinary. Okay. Now, so that one is easy to understand. With this one, we can do something straightforward. So here are 2 straightforward examples. First, look at this padlock. Combination padlock has 3 rows. Each row has 10 numbers, 0 to 9. All right. Now each has a code. So if you understand this principle, how many 3-row combination padlocks will guarantee 2 of them have same code? If we have many, then some padlock will have same code. So you should not be surprised if someone else has same code as your padlock, because the number of different combinations is only 1,000. 10, 10, 10, only 1,000. So these are boxes, 10,000 boxes. In order to guarantee some contain two codes that are the same, that means we need at least 10,000, more than 10,000 padlocks. The smallest number is 1,001. If we have this many padlocks, then it's guaranteed at least 2 padlocks will have same combination code. So that's a straightforward application of pigeonhole principle. All right. Second straightforward one is for students in this class, 140. How many will have same birth month? How many will have same birth week? So here, again, it's a straightforward application of pigeonhole principle. For birth month, k equals 12, boxes are months, 12 different months. So we have 140 for 12 months. So 140 pigeons, 12 pigeonholes. So it's give us how many? 12. All right. Now for birth weight, there are 52 weights. So pigeonholes are 52, and pigeon again is 140. So 140 divided by 52, take the seeding, so that give us 3. You see, it's quite straightforward, very easy. All right. So it's very easy to use. So these are 2 trivial examples. Now I will give you a few more not simple examples, and followed by some not trivial examples, elegant examples. All right. Okay. Oh, sorry. Let me bring up the time. I forgot to set the time. Let's go. Okay. Yeah, I set up a clock to remind me of time. Okay, so that's good. Everyone understands this principle, right? It's very straightforward. Now let's use this principle to prove something interesting. Yeah, again, something strange happened to the whiteboard. Usually it's easy to erase, but before that, I clean the whiteboard, maybe because coating of this liquid. So it's not that easy to erase now. Let me try it. Oh, maybe because the brush, old one is better. This one is broken actually. All right. So pigeonhole principle typically allow us to prove the following. We want to prove that some structure X exists. So we want to prove some structure exists. So there are some elements satisfy certain property. So that's property X. All right. So pigeonhole principle are very useful to prove such a statement. Okay. So first, non-trivial example, a simple example I will give you is the following. Okay. So we have circle of radius r. I want to show you that if we have more than at least 7 points inside the circle, then the claim is there exists 2 points P and Q whose distance is at most r. How can we prove it? Look, pigeonhole principle very, very simple, but the problem is where are the pigeons? Where are the pigeonholes? That's a problem. The key in using pigeonhole principle is to actually 3 things: to find pigeons, to define pigeon and pigeonholes, and an assignment from pigeon to pigeonhole. These are 3 main things. Okay. So these are 3 main things. Usually, the first one is simple. Usually, it's very obvious. So here, it's 7 points. These are pigeons. Now pigeonholes. Actually, we don't have any pigeonhole at all, just a circle. All right. So we need to find the pigeonholes, or to construct the pigeonholes, so that we can apply the argument. So how we construct pigeonholes? For this particular case, we constructed 6 pigeonholes as follows. Maybe this is in the middle. Yes, that's about it. Now it's quite easy. We divide the disk into 6 parts. 1, 2, 3, 4, 5, 6. So degree equally. Okay, so the degree is pi over 6. Pi over 3, sorry. I think 60 degrees. Degree is 60. All right. Now, within each section, for any 2 points, its distance is at most r, by the property of circle. Now we have 6 pigeonholes. We have 7 pigeons. That means one pigeonhole, regardless of how we put these 7 points inside the circle, they are the circle, the 2 points lie inside. Then their distance is at most r. So this, maybe we put points like this. So for this section, these 2 distance is at most r. So that's a simple application of pigeonhole principle. Okay. All right. So here the structure are the structure S are 2 points. The 2 points. Okay. All right. Now I give you 10 numbers. Oh, this one has some connection with the homework. One of the homework question. I have a set of I have a set of positive integers. Okay. I forgot to in the homepage message the set of positive integers. I want to determine number of subsets whose sum equals k. Okay. So that one is related to this one. So here I give you 10 numbers. I want to say that this set contains 2 subsets. Actually, I want to say 2 disjoint subsets. With equal sum. So such that sum are equal. Maybe this will call to 1. All right. So I claim that for these 10 elements, 10 integers, I can always find 2 disjoint subsets with equal sum. For example, for a very small example, say 2, 6, 1, 7. For example, 4 numbers. Then I have 2 different, this one and this one, they have equal sign. Or maybe I can even one more, so it's not really partition. So if I have these three, I have 2 subsets. This one, they're some same. So all add up to 8. Okay. So how can we prove this one? Again, this one does not seem to be have anything to do with pigeonhole. Actually, we can use pigeonhole principle to prove it. Now, where are the pigeons? Where are the pigeonholes? Where are the pigeons? Where are the pigeonholes? So here, pigeons, actually, even pigeons are not obvious. Where are the pigeons? Pigeons, in this case, are subsets. Subsets of S. So in this case, number of subsets 1024. Total number of subsets of these 10 elements, there are 10 elements, it's 1024. So now we have pigeons. All right. So each subset get a value, which are positive numbers. Now we look at these values. How many possible values can subset take for a sum? So if we sum up these numbers, for these 10 elements, I believe the way I give you certainly it's less than 1024. Total sum of S is less than 1024. So what can we say about that? So we use these 1024, these number total sum, the connection number of these sum of these subsets will be less than this one. So we have a number of pigeonholes that's less than 1024. Number of pigeonholes. So that's number of pigeonholes. It's less than 1024. So by pigeonhole principle, what can we say? Some pigeonhole will be occupied by two pigeons. So some number will be sum of two subsets. So what we can say is some number is sum of two pigeons of two subsets. So there exist subsets. Let me instead of S, uh, so we know there are two subsets with equal sum because of pigeonhole principle. Because subsets sum, all of their values will be less than 1024. So because but we do have just many subsets, so two of them have to agree. All right. Now, one thing different is here we want to disjoint subsets. Here it just give us two subsets. Maybe the answer here is maybe two, not for this one. Okay, so we may come up with the answer. So these subsets have same yeah, has same value, but they are not disjoint. The thing that these two subsets have to be disjoint. So that's very simple. Once we have these two subsets, what we have that's S1, that's S2. So if we want disjoint one, this is their common part, that's same. So we just take this set and this set. Now they're disjoint and have same sign. So these two are simple application of pigeonhole principle, simple applications. The key point is to find the pigeons and construct pigeonholes. So that may not be trivial. Okay. All right, let me see time. All right, next few examples are more involved, and some of them are quite elegant, actually. Once I tell you, it's not difficult to understand. But it's not obvious, but I hope I will explain in such a way that you can understand it. All right. And the next one is so given any set of n plus 1 integers, I can always find two integers, x and y, such that x minus y is divisible by n. So for example, let me give you something, maybe 5 integers. Okay, we have 5 integers, so n equals 4. This statement says I can always find two integers here whose difference can be divided by 4. It's a multiple of 4. All right. So in this case, these two, 17 minus 5 equals 12, which divides 4, which is divisible by 4. So that's the meaning of this statement. For any set of n plus 1 integers, I can always find two integers such that their difference is multiple of n. Why is this the case? So we are the pigeons. We are the balls. So these will be balls or pigeons. Now, what are boxes? It's not clear at all. It's not here, right? We don't see boxes or pigeonholes. We only have pigeons. So we need to construct boxes. So we have to look at this property. When is x minus y is multiple of n? When our difference of two numbers can be divided by 4 without nothing left. So we look at their reminders. When 17 divided by 4, its remainder is 1. When 5 divided by 4, its remainder is 1. So when their remainder, when divided by 4 are same, their difference can be divided by 4. So what we need to do is, first one saying that exist two integers such that x modular so when x divided by n, so the remainder it will be same as y divided by n. So this one same as this one. Now we send something, right? In pigeonhole principle, we want something to be equal. So here we're looking for something to be equal. The remainder will be same. So what we do is map an element. So here we construct the mapping, the function of the mapping assignment. So for element x, we put it into O x mod n. So for each element, we put it into whole the box number x mod n. So in case of 4, so here will be box number 2, box number 1, 1, here 0, here this one is 0. Many different value for reminders, only n different value for reminders from 0 to n minus 1. Now we have n minus 1 integers. The n minus 1 balls, number of boxes, and only n boxes. Therefore, two boxes. There are one box that contains two numbers. So that means two numbers will have the same remainder when divided by n. So namely for this particular case, this one. So these two numbers have this property, therefore it gives us this property. All right. Okay. So this example. Okay. Let's see. Do I need them positive? I forgot whether I think it's positive. No need for zero. Yeah, positive integers. If we take n plus one integers from 1 to 2n, all right, then what we can say is we can always find two integers, x and y, so that one divides the other. So let's say maybe n equal, n may be set to be 5. All right. So we arbitrarily choose 6 integers from 1 to 10. N plus 1, choose 6 integers from 1 to 10. Arbitrarily choose what? I don't know what they are. Maybe 3, 5, 7. Oh, only 1 to 10. Okay. 8. It seems to be quite obvious then. 8. Okay. So here in my choice, I choose 6 integers from 1 to 10. N plus 1 is, I only need 5, n 5, yeah, choose 6 integers. Then claim that there exists 2 integers, that one can be the other. So in this particular case, indeed, we should see these 2 integers, 4 divided 8. All right. In this case, again, it's quite obvious. So these are pigeons, but it's not obvious at all. Where are the pigeonholes? It's not obvious at all. Okay. So in that case, what should we do? So let's see, do I use AI or XI? I forgot in the notation. Oh, XI, okay. So let's set for integers, so let's use S. So for XI, each member in every integer can be represented by a number P I. Pi is all the number. This is all the integer. This part is a multiple. It's a power of 2. And any integer can be represented in this form. But what we do, keep on dividing it by 2. So eventually get a power until it's all the number. For example, let's see. A 40. Number 40, okay. Number 40. Number 40 can be represented in this form. We keep on dividing it by 2, so that's 2 times 20. So don't keep on divided by 2, 2 to power 2 times 10, 2/3 times 5. So that's the PR. The integer can be represented in this form. Okay. Now, what's the range for this PR? So that's key point. What's our range of this PR? Pi are all the numbers in this range. So from 1 to 2n minus 1. How many are there? Number of all the integers in this range at most only n possibilities. Okay. Now here are pigeonholes. Now we have pigeonholes. So we have n possibility. Each cell has a pigeonhole. A number, an xi will map to pi. Assignment is xi mapped to pi. The mapping is from xi to this one. That's our mapping assignment. Pigeonhole says for any mapping, any assignment, the party holds. Now for this particular mapping, of course, same party holds. Okay. So what does that mean? The pigeonhole principle, there exists xi, xj, such that the representation 2ki, pi, 2kj, pj, this is the representation for these two. Okay. So in this case, these two are safe. Pi equal pj. Pigeonhole says that some pigeonhole will be occupied by at least two pigeons. So in this case, these two values are equal. Now I have two numbers of the following form. So now we have two numbers of the following form: 2 to the power of ki times p. Another number is kjp. So these are safe. All right. Now suppose ki less than kj. So one of them will be smaller, of course. Then this one divides this one. Because this one, if I multiply by, this one divides this one equal 2kj minus k. So that one multiply this one, give us this one, these PSA. So there's another example showing that it's not trivial to construct pigeonholes. I see some information, some information to try, take a look and then come back. Okay. All right. Okay, so this one has to do with grids on the plane. So once we have grid, so evenly spaced, then these points are called the grid points. So these are called the grid points. All right. So once we have two grid points, say these two grid points, then there are line segments between them. If I link them together, then it's a middle point. So this one is a middle point. Maybe with different color. That's called a middle point. All right. So middle, then for any two points, grid points, I can link them together. Then the line segment has a middle point. The middle point can be a grid point, as in this case, or may not be a grid point. For example, so this one is a grid point, but this one, of course, is not. The middle point is here. All right. Or even it's a straight line, it's a vertical or horizontal line. So these two. So this middle point, it is not. So this one has to deal with grid point. The thing is, if we have 5 points, 5 grid points, for any 5 grid points, I can always find 2 grid points whose middle point is also a grid point. That's a statement. A 4 is not enough. 4 is not enough. For 4, it's quite easy to see 4 is not enough. I can give you these 4 grid points. Okay, there are 6 different combinations. So for these 2 middle point here, middle point here, middle point here, and for these 2 middle point in the middle. So none of them are grid points. So actually, this is really we need 5. Okay. But whenever you give me 5 grid points, I can always find the 2 grid points, such that middle point of these 2 points is also grid points. It is also grid point. So why is this the case? So we have the pigeon. Of course, usually pigeons are very simple. So 5 grid points serve as balls or pigeons. The difficult part is find the pigeonholes. What are the pigeonholes? These are not pigeonholes. They look like pigeonholes, but they are not. All right. So in order to do this, what we need, I think, we need maybe 4 pigeonholes. Then 2 grid points will have certain property. Because 4, the 5/4 will be 2 points, will be in the same pigeonhole. So that's what we need. So let's take a look. What is required for middle point to be a grid point? So for this purpose, it's convenient to use the Cartesian coordinate. So label each point by its coordinate. So maybe here is 5, 7, for example. But this one maybe even more. Let me just put it here. Maybe here have 0, 0. So that's 1, 2, 3, 4, 5, 6. So it's 3. Okay, so then this one is just 2. It's convenient to do it in this way. Okay, so each has a coordinate. Now, under what condition the middle point is also a grid point? So given 2 points, their coordinates, say x1, y1, and x2, y2, 2 points. What's the coordinate of their middle point? The coordinate of their middle point, what's coordinate? It's very easy. It's the average of x1 and x2. Here is average of y1 and y2. That gives us the coordinate of their middle point. All right. Now, in order for this one to be a grid point, what we need is this one and this one, both are even numbers. When both, because divided by 2, so when both of them are even numbers, then their middle point is also a grid point. All right. Now, when the summation of 2 integers is an even number, so that's the parity of a number. A parity of a number can be even or odd. Say let's use 0 to denote even number, 1 for odd number. So parity will be either 0 or 1. All right. So in order for the middle point of 2 points to be also grid point, the parity of these 2 numbers must be same. in order to get a grid point. Otherwise, it cannot be grid point. All right. So that will be sufficient to use even odd pattern instead of actual numbers. So here is palette pattern. We use palette pattern. And pigeonholes. All right, there are four different patterns. If I only zero one, so we have 0, 0, 0, 1, 1, 0, 1, 1. So these are pigeonholes. We have palette pattern and pigeonholes. Now for any 5 points, they give any 5 grid points, but not matter where we put them. Okay, so we have these 5 points. Here can be erased. All right. So since there are 5 pigeons, there are only 4 patterns. Two grid points will have same kind of pattern. All right. So once we have same pattern, then here will be even number, here will be even number. So when we divide the two, that give us integers. So for example, maybe 2 of this pattern. So 2 points have this pattern. So then their middle points will give us grid points. So for this one, we can just mark it. So here it's, let's see, just work out of this example. So pattern is 0, 1, okay. Here pattern is 0, 0, here 0, 1. So 0 is sorry. 1, 0. All right. So for these two, for these 5 points, we see these two have same pattern. 0, 0, 0. So then their middle point is different middle point. And I think we don't have time for the next one. It's more involved. So the last one, please take a look at this one to see if you can understand it. I will see whether we'll talk about it or not next week. Next Wednesday, next Monday is a holiday, right? Okay. Okay, so that's it for today. But before that, what I would like you to help me to do is do a test. Submit your homework in 1 or 2 minutes. Okay, please prepare to get your file ready. In about 1 minute, I want you to submit it through course homepage. I want to see how fast whether the system has capacity to handle it, because the midterm exam and the final exams. I want to use it for submitting your answers. All right, let me test things out. It's not open yet. Okay, I will do it in about 1 minute. Let me open window to see whether it's ready. When when I tell you to submit, please submit. Okay. Okay. So let's just do it. I give you maybe 30 seconds to get things ready. Okay, for submitting homework too. Okay. Yeah, when I send you send out in the chat, submit now. I also announce it. Please submit as fast as possible. Please try to submit now because I want to see the system capacity. Okay. Of course, you can submit until 5 p.m. All right. Yeah. Okay. Please submit it now. Okay. It's ready now. Yeah, please submit to the system. I want to see how fast it works. Whether it can handle it or not. Oh, it's very fast, you see. A few seconds. Okay, I got 20 submission already. So it should be okay, I think. Oh, wonderful. Thank you. Yeah, it seems to be okay. I got about 30 submission in less than a minute. We should be able to handle it, I think. All right. For homework one, I asked the TA. They told me they will finish marking by this week. I asked them to send the email. I sent back your homework, marked one, to you by email. Okay. No type of page in homework two. It's a new one, not homework one. I can see all the files submitted. Maybe you have to refresh it in order to submit to the submitted files. I can see it. All right, sorry, I must have that I'm not familiar with other different ways. Okay, I just try to find a simple way to do it. There could be other ways instead of doing it manually. If you can help me, then I will be very happy to do it. Okay. I'm really not familiar with these things. It's really beyond my capacity. I'm I only have very basic knowledge of how to use these kind of things. So it seems you don't have congestions. No, the title is homework two, not assignment one. Or inside, maybe, oh, sorry, inside, maybe inside I did not forgot to change it. It's possible inside. Or inside it said assignment one, sorry, yeah, actually that should be assignment two. I forgot to change it. Okay, that's easy, I'll change it. Yeah, inside, okay. Sorry, thank you, yeah, yeah, okay, all right. Yes, the video quality, I really don't know how to do it. Monday, I re-recorded last 10 minutes when no one is here. It seems the quality better, maybe because of bandwidth problem. Actually, technician told me maybe because of bandwidth. Okay, for that I can do nothing. Because when a lot of you are attending, the bandwidth lowered. So if the resolution too high, then the speed you will not be able to receive these things in time. Therefore, the bandwidth lowered down. Okay. Yeah, tomorrow the team will discuss solutions for homework one. To homework two. Oh, sorry. Yeah, tomorrow we'll discuss homework two solutions. Okay, solution has been discussed last week or the week before, I believe. Because I told them to discuss solutions. Sorry, Ben, you said not discussed at all. What do you mean? Homework one? Oh, really? I asked them to discuss solutions. Uh, I will ask the TA again, okay? Your TA should ask your email, but one problem is they may not read the email every day. As a thing for me, I cannot read the email every day. I don't have computer at home. I don't read the emails. Only when I'm in my office, I read the emails. So every other day or something, depends on when I come. Okay. Yeah, it seems that it forgot to upload the solution. I asked my TA to do so. Okay. Okay, I think that is for today. Yeah, I just checked out the tutorial part. I did not see homework for week 6. I will ask the TA to upload these things. All right, that's it for today. Okay, bye. See you next Wednesday. Okay. What's your language, Ben?